To move into the actual identification of our connective tissue, we need to start with identifying the embryonic connective tissue, mesenchyme. This embryonic tissue, this mesenchyme, is what will differentiate into all other connective tissues. It's what will create the 4 different categories of our connective tissues. It'll help make all the tissues in our connective tissue proper, which we'll talk about in this video. It'll make our different cartilages, we'll cover in this video, as well as our solid connective tissue, osseous tissue, we'll do that in the next video, and then our liquid one, which is also our vascular or our blood. We'll do that in our next video as well. So we have 2 different videos to go through. Here we're starting though with the mesenchyme, connective tissue proper, as well as the cartilages. So we already know that the mesenchyme is going to have its function as differentiating into any connective tissue. Basically creates all of them. We know its location is embryonic, so in utero, before birth. And identification-wise, we're looking at the individual cells. So we have a cell here, cell here, cell here. Those are all the individual cells. Now you still have some normal gel-like matrix. You still have fibers. So it's the same basic categories. But this one's so unique because it differentiates into any connective tissue. So now we move into the actual connective tissue proper. This is our areolar connective tissue. Areolar connective tissue falls into the connective tissue proper category, and more specifically, connective tissue proper can be broken down into a loose and firm or dense gel matrix. What that means is the loose gel matrix isn't liquid, isn't really solid, it's kind of in between. Think if you're making gelatin or jello. You start off with pure water, very liquid. Once it's set, it's solid, you can cut a square out and it stays that square shape on the table. We're in between the two. We're in that area where it's more viscous, it's thicker, but it's not quite solid. What if we tried cutting a square out and putting it on the table? It would kind of just ooze out, it wouldn't hold shape. That's this loose gel matrix inside the connective tissue proper. So the areolar connective tissue. Now in areolar connective tissue, we'll see all 3 fiber types visible. We'll have the very thick and strong collagen fibers. You can see there's a nice thick one right here. That is going to be the thick collagen fiber. We then have the thinner reticular fibers, still made of collagen, but thinner. There's one over here, for example, one running here. Those are going to be the thinner, actual, more reticular. And then we have the dark ones, elastic fibers made of elastin. Here's one right here. You can see the color difference helps with identifying that's more of an elastic for elastin. The way we identify is by seeing all these fibers in this really haphazard jumbled mass that is areolar tissue. The location for areolar, you can see here it says widely distributed under epithelia. Probably one of the easiest places to think of is in your skin, the dermis of your skin. So the top part you're touching, that's the epidermis. That's stratified squamous. But just below that, in the dermis will be areolar. It'll be supporting the epithelial tissue above it. It'll be providing nutrition and gases, so exchange, diffusion. Which gives the function wrap and cushion, makes sense. It can wrap around underneath the skin. It wraps around hollow organs. So this is your areolar connective tissue found in the actual connective tissue proper. Adipose. Now in adipose, you can see in this tissue, this is one adipocyte cell, CYTE. This is a second adipocyte, a third adipocyte. With adipocytes, they're basically a specialized variation of the fibrocyte. So what we're looking at here now is going to have these specialized cells with their nuclei off to the sides. These are the nuclei. They're all pushed off to the sides because every bit inside the cell is filled with lipids or fat. So all that white you're seeing inside the cells is pure lipid. The way to differentiate, because you might say these kind of look like your these kind of look like your simple squamose. Well, notice the nuclei. Simple squamose, the nuclei is right in the center. In the case of adipocytes, the nucleus is off to the side. That's the biggest giveaway. So what's the function? Reserve fuel source. All that lipid is an energy source your body can pull from if necessary. You could have this as cushioning, insulation as well. The lipid helps with cushion impact. Insulation is under your skin, in the hypodermis of your skin. So it helps to conserve body heat. So location, I mentioned under skin, that's the hypodermis. But you can't just say the body for location. You have to give areas of higher concentration. Hence the underskin, higher concentration, could look around the kidneys because it has a higher concentration. The abdominal region usually has a little bit higher concentration. Have down here breasts or mammary region. That's male or female, can have a little higher concentration as well. So we have location, we have functions, and we have identification. That's your adipose tissue with the adipocyte cells. Now, the reticular tissue, this is the third tissue and what will round out the loose gel matrix part of the connective tissue proper. So we had areolar, we had adipose, now we have reticular. Those are the three that fall in that more loose gel matrix part inside of the connective tissue proper. You can identify reticular based on the reticular fibers. All of these dark black lines, those are all the reticular fibers. And in between all those pink dots, those are reticulocytes. So they're specialized cells found in your reticular tissue, reticulocytes. So this tissue itself makes kind of like a framework. One location you can find it is the spleen or the lymph nodes. Now these different organs, they're not going to be very solid. You can press on them and you can squish. So this isn't a very rigid framework, but it helps to create the shape, more of a delicate framework, delicate network that helps to keep those tissues in their proper shape and function the way they should. So this is your reticular tissue. Now after reticular tissue, we're moving into dense regular. We're shifting from the loose gel matrix to that dense or firm gel matrix. This is all still within the connective tissue proper though. The thing that should stand out, all of these collagen fibers, they're all running in parallel. So we have dozens, if not hundreds, of collagen fibers all running in parallel to each other. So that's the big key giveaway on this one, is we have all of these collagen fibers all in parallel fashion, which means there's a lot of strength in the direction the fibers are going. But if you go in the opposite direction, let's say all the fibers are running up and down, if you pull sideways, there's not much strength at all. So this is going to be your dense, regular connective tissue. Location, tendons and ligaments. Tendons, bone to muscle. Ligaments, bone to bone. There's a lot of strength in the direction the fibers run, but not much strength in the fiber directions they don't run. So it's helping with the function of attaching bone to bone or attaching bone to muscle. So again, bone to bone, ligament, bone to muscle is tendon. This is your dense regular, falling more in that dense gel matrix or that firm gel matrix inside the connective tissue proper category. Now keep this in mind. Look at the dot pattern, how you have all these parallel fibers. Now look what happens. Dense irregular. Do you see any pattern? No. The fibers are going in all different directions, hence the irregular name frame. Dense irregular connective tissue is still part of the connective tissue proper. It falls under that dense or firm gel matrix because of all the collagen. But now with the collagen running in all these different directions, there's not strength in just one direction. There's strength in any different direction that it runs. Which means this gives more strength in multiple directions, but doesn't have the same maximum strength as that dense regular we just looked at a second ago. So where can you find it? Well, this is one of the main parts of your dermis of your skin. So we have the epidermis, stratified squamous. Then we have the next layer down is the dermis. Now, if you remember, we said that areolar connective tissue is in the dermis. That's true. We have a little bit of areolar and then a whole lot of dense irregular in the dermis of your skin. Other locations, you can see it has fibrous capsules of joints. Help us contain around the joint. Keep and maintain that joint cavity. Also have submucosa of the digestive tract. Well, submucosa means it's below the mucosa. The mucosa is going to be epithelial tissue. This can help to surround it to provide some strength to your digestive tract. So really, what's the function? Withstand tension in many directions. Sure, we kind of said that. Because we said that all these fibers are running in different directions, it gives strength in all directions. So this is your dense, irregular connective tissue. And then we have elastic connective tissue. It's going to be important to call this elastic connective tissue because we're going to see an elastic cartilage in a moment or two. So this elastic connective tissue, I kind of did a little labeling here because only that little dark squiggly part here. What you're looking at, this is going to be an artery. And around that artery, besides the smooth muscle, the epithelial tissue, and everything else, we have a little bit of this elastic connective tissue. It's going to help with stretch. Because as your heart beats and pumps blood into the major vessels, all that increased blood causes the vessel to stretch just a little bit. Elastic connective tissue helps with the recoil to bring it back down after the beat. So we have some flexibility here, allowing recoil up from the tissues. I already mentioned the location was in the large arteries, but it can also end up a little bit in the bronchial tubes. Bronchial tubes, think inside the bronchi, so in the lungs. So this is your elastic connective tissue. It's the final or third one of the dense or firm gel matrix inside connective tissue proper. That means we've gone through 6 different tissues of connective tissue proper now. We have the 3 that are the loose gel matrix. That's going to be areolar, that's going to be adipose, and that's then going to be the reticular. The firm or dense gel matrix, which these are more solid now, that's the dense regular connective tissue, the dense irregular connective tissue, and now elastic connective tissue. All of these, though, are connective tissue proper. So let's move on to the next category, cartilage. In cartilage, there's going to be a total of 3 different cartilages we're looking at. But in all these, the key thing is they stand up to compression. They stand up to tension. You can have cartilage in your joints as they smash together. You can have cartilage in your nose, in your ear. So a lot of different compression and movement, but also maintaining shape. They're the intermediate between the dense connective tissues and then the solid, the bone. So that dense regular, dense irregular we just talked about, that was part of the connective tissue proper. This is kind of a step up, a little bit more solid, a little more firm. But it's not solid as bone, which is the osseous tissue at this point. And then the interesting thing, they lack nerve fibers and they're avascular. What that means is the cartilage itself doesn't have any innervation. There's no nerves. There's no pain in the cartilage. So if the cartilage would cut, you wouldn't feel any pain. You think, hold on, I've torn cartilage. I know so-and-so that tore cartilage. That hurt. Well, yes, it definitely can. But it's the surrounding tissues that hurt, not the actual cartilage itself. The cartilage doesn't have any nerve receptors. It's not innervated. So when you tear cartilage, more often than not, you damage the tissue around it as well. That surrounding damaged tissue, that's innervated. That's going to hurt. And the avascular, without blood. Without vascular blood. That means all the blood, all the nutrients, all the gases must diffuse into the cartilage. All the waste and byproducts have to diffuse out. That's one of the biggest reasons why an injury to cartilage can take so long to heal. Quite often, a cartilage injury might take longer to heal than an actual bone injury or break. Because bone, osseous tissue, is vascular. It has blood. But here in cartilage, the blood has to diffuse in, so all the healing has to diffuse into the damaged points to repair and make it back to what it was. Ground substance, looking at collagen and elastic primarily. Because collagen is strong, elastic flexibility makes sense. Your cartilages are meant to withstand high tension and pressure, but still have some give or movement. Put up here chondroblast and chondrocyte. Blast. Remember, blast is an immature cell. It's forming, it's making the cartilage. While the chondrocyte is maintaining the cartilage. So that's the ones that are staying healthy in adult tissue. But those chondrocytes are found inside lacuna. Lacunae. Basically, these lacunae are going to be structures that are around the actual chondrocytes. So it's kind of like the chondrocytes are living inside lacunae. So this white part, that white part inside that circle, that is going to be an actual chondrocyte. But the darker purple ring around it, that ring of purple around it, that's lacunae. So you're looking at chondrocytes inside lacunae. And that's found across all three cartilages. So let's look at the first cartilage, hyaline cartilage. Now, hyaline cartilage is the most common of the cartilages. You're going to see this, and the key giveaway here is in the matrix. So that space between the cells. It's purple, but you don't see any fibers. So if you see a cartilage, so chondrocyte and lacunae, and there's no fibers in the matrix, that's going to be your hyaline cartilage. Now, locations for hyaline cartilage could be the embryonic skeleton. So in utero, as the bones are forming, they don't start off as bone. They start off as hyaline cartilage. Then the osseous tissue comes in and replaces. So embryonic skeleton, we have it at the end of our long bones. So the ends of your long bone, like the humerus, the radius, the ulna, the ends of those bones have cartilage helping prevent impact. You're going to have ribs, nose. Well, your nose, the tip, is made of cartilage. The ribs come around. They join to the sternum via cartilage. So it's found throughout the entire body. What's its function? What's it doing? Supports and reinforces. So supporting and reinforcing. Makes sense because you are supporting the ribs to the sternum, supporting the joints as they come together. So it supports and reinforces. This is your hyaline cartilage. Now notice the histology here. Again, no fibers in the matrix. Compare that to elastic cartilage. Notice elastic cartilage. You're seeing the fibers in the matrix. So in the elastic cartilage, you're able to see the fibers. You're seeing those elastic fibers in the actual matrix. So that's the dead giveaway here. Where can you find elastic cartilage? Well, it's in the external ear. It's that part that goes around the outside, giving it its shape. It's in the epiglottis. It's that part in your throat. You have your trachea that carries air down. You have your esophagus that carries food and water. The epiglottis is a flap that covers. So when you swallow, it folds over the trachea, blocking the airflow path. By blocking that pathway, it makes sure food and water does not get into your lungs. When you're breathing, the epiglottis is up. Swallow any food or liquid, it forces it down so it doesn't go in your lungs. So your elastic cartilage here, maintaining shape with flexibility. Both the external ear and the epiglottis are going to have a shape. It can bend, but it always goes back to the original shape. So that is your elastic cartilage. Now take hyaline cartilage, take elastic cartilage. Compare it to fibrocartilage. In the case of fibrocartilage, you're noticing you still have chondrocytes in lacuna. But they're spread out a little bit differently. There's a different arrangement here. This fibrocartilage is going to have more collagen in between, which means the matrix is denser, it's more full of collagen. Location-wise, you can see here, intervertebral discs. That's what's in between each vertebrae, each part of your spine as you go down. Each vertebrae has cartilage in between, helping to cushion it. You have menisci of your knee. Menisci in the knee, think wedges out in the knee. It's helping to make sure that your knee doesn't just slide out of placement. Menisci can help with alignment, keeping your knee in place. So you have these cartilage wedges in your knee helping to align. So the action, well, tensile strength is a big one because of how much you have of collagen here. Shock absorption makes sense. Each vertebrae going down is going to have these little shock absorbers. Each step you take sends a little bit of shock going up the vertebral column. Each one dampens that, so by the time you hit your head, you're not having the same shock impact that your hips are absorbing. So this is your fibrocartilage. So that's the connective tissue proper and the cartilages. We have to go into the bone, which is made of osseous tissue, solid, and go into blood, the liquid connective tissues, in the next video. So we have 2 down, 2 more categories to go.